And you're on.
Okay, thank you. Hello, I'm presenting my paper titled Beam Switching for Millimeter Wave Communication to Support High-Speed Trains. This is a joint work with Dr. Shannon from Qualcomm and my supervisor, Professor Robert Heath. These photos show some of the high-speed trains that are coming out in 2015. High-speed trains are expanding rapidly. Currently, there are around 23,000 kilometers in operation as of September 2014, and this number is expected to double by 2025. Providing broadband services to this high-speed train will be very essential in adding more value to it. For example, passenger could work on the train as if in their office, if they could connect to the internet, get their document from the cloud, for example. And they could also entertain by watching videos or some other entertainment available on the internet. However, currently the deployed system have relatively have quite limited rates. For example, one system in Europe called Mobile Broadband Global Link System, it can support only up to 4 megabps in the downlink and 2 megabps in the uplink. There are different systems deployed at in different parts of the world, but they come up to around a few megabps. And this number has to be divided, has to be shared among the potentially hundreds of users on the high-speed trains, and so the rate is very limited. So one of the potential to support such a high data rate broadband service would be to go to millimeter wave, where we have a large amount of spectrum available at these frequencies. So one of the current advantage right now is that CMOS technology has reached a mature state that it can produce low-cost millimeter wave devices, and this this is evident from the fact that a 60 GHz Wi-Fi system, for example, 802.11ad chips, are already on the market. However, there are several challenges in using millimeter wave. That's related to the mobility and also the characteristics of the millimeter wave itself, where it has a small, due to the small antenna apertures, it will experience a large path loss, and so we will need directional beamformings. And to do that directional beamforming, we need the beams to be aligned, to be properly aligned, and that to keep that aligned in the mobile environment is challenging. And one of the solutions that we think is a potential one is to do beam alignment based on beam sweeping. So, which is shown here. We propose a architecture for this type of high-speed trains, where we have we assume that the base stations are installed uniformly along the rails, and the antennas on the train is on the roof. It's not inside the train. It's on the roof. And so one of the things to note in this scenario is that there always be line of sight, because there's nothing, no other thing that will obstruct the train, the top of the train and the base station that is sitting next to the rail. So what this means is that if you have line of sight to point the beams, what we need is the position of the train. And the position of the train can be obtained from the train control systems, where they use this for security purposes, for scheduling train, etc. And that gives us the opportunity to leverage that and do it to help in doing this beam switching to get efficient communication system. So our contribution is listed, is shown here. We first we will show that the potential, the conventional beam sweeping approach that is used, for example, in the standard 802.11ad, will not work well due to the Doppler spreads, which is which the use of quasi-omni will suffer from. We then propose the architecture as shown in the previous slide, with a beam switching approach as a solution to realize efficient beam alignment that is that is good for these high-speed train applications. We then study the trade-off based on this architecture. We study the trade-offs of the choice of the beam width and the position estimation error. And the conclusion there is that the wide beams will suffer low gains, while narrow beam will suffer position error. There is one prior work that we should mention here. This work here, shown at the bottom, they also study a similar architecture. However, they study only the frequency to redo the beam sweeping, while our approach here, we choose a beam switching approach that we don't need to do beam sweeping or any beam training at all. So here, this slide shows the limitation of the beam sweeping approach. To give some background on how the beam sweeping works, here it is shown in this figure. Here, the station 1 here is training its beams with the help of station 2. What it does is it just transmits from all its beams here. You have 3 beams here, sequentially 1, 2, 3, and then the other side, station 2, will just listen using quasi-omni receive beam pattern, because it does not know where to point it does not know where to point. And after station 1 finish transmitting on all its beams, station 2 will feedback to tell station 1 which one of the beams that it heard the most, that had the highest strength. At this point, again, it does not know where to point, so it has to use quasi-omni patterns. And station 1 also has to use quasi-omni pattern for this reception, because it does not know where to point yet without the feedback. And with that, we can use this quasi-omni pattern, so it has to be able to decode the packet using this quasi-omni pattern. And and to do that, we need to estimate the channel. And so what the relevancy here would be what is relevant here is the channel coherence time. So we want the channel coherence time to be much larger than the packet length to be able to decode it. So with that, we compute the coherence times as a function of this beam width of the quasi-omni pattern. So we use this result from the 2000 based on this paper by Dr. Durgan, and the result is plotted here for different beam width here: 180 degree, 150, 120, and 90 degree. So, and the packet length, typical packet length here, is computed from the packet length defined by the 802.11ad using the control phi here, which is around 15 microseconds. So to be much larger here, I assume it to be 5 times the packet length, which is this line here. So with that, we can see that how much, if we assume a certain beam width, what is the maximum speed that it can support. And the result is shown in this table here. You can see that if you use 90 degree beam width for quasi-omni pattern, you can support up to at most around 40 meters per second, which is far below the range of the speed of the high-speed train, which is around here between 70, which is more than 20 meters per second. So we can conclude that quasi-omni pattern is the bottleneck here that would render the beam sweeping unlikely to work. So for our next step is we want to quantify some trade-off between the choice of the beam width and the pointing and the estimation error, the position estimation error. And here I will explain the step to do that. And our objective there is to maximize the data rate. And so the first question is, how do we compute the data rate based on the proposed architecture? So here we use the Shannon capacity formula to compute the rate, which is given by this well-known expression here. And this SNR is the instantaneous SNR at each location where the train passes the coverage of the base stations. And it's defined as here, and this received power will be defined in the next slide. And our optimization problem is shown here. Basically, we'll be optimize over the beam width and assume that the number of beams n is the number of beams in the coverage, and so this for a fixed number of this, then we want to find the beam width here, and this number of beams is also a function of this theta. So we will compute the optimal over all of this, and that means also all over this n for any number of n2. So here the average here is based on the average of the speed errors, which we will define in the next two slides. And this is just the time. This is just the time that the train takes to pass the coverage of the base stations. And this D, which we will show the formula later, is the total amount of the data received while it is in that the coverage of the beams. So this showed our link budget model. We use the path loss model, the log distance path loss model, the typical one, with as shown here, and these terms, which have the transmit power plus the transmitter antenna gain in the in dB scale, is what is called the EIRP, which is the effective isotropic radiated power. We assume that this term is constant. This term is actually limited by regulation to be less than 40 dBm, and so we think that it would not have you would not have much flexibility in changing this. So we just fix these terms. And so with that, we arrive in this. The received expression can be written as this, with this A related to the EIRP and the shadowing margin. And this is the receiver beam width, the receiver antenna gains, with the beam width of the receiver here represented by theta B. And this terms here is the total distance between the transmitter and receiver at a given time. And the noise model is given as here, which increases with the beam width, and we also added noise figure to represent the implementation loss of the hardware. So our position prediction here, we assume a model as given here. So the background for assuming this model is the observation that from physics, we know that for a large mass train to change speed, it's difficult to change speed for the train because it has a large mass. Because of that, it's really likely that the speed of the train, when it passes through the coverage of one base station, which is around 100 meters, it will be more or less constant. With that, we only assume that the speed error will be coming from the estimation error of the whatever the device that they use to estimate the speed of the train, and that error is assumed to be Gaussian. And with that, we just use the estimated speed to estimate the position and then calculate the switching timing. So with all this model, we can now compute the average rate. And the first is what we do here is we compute the total amount of data that you can receive when you pass by when the train passes by a beam. So we use this diagram. The first one is the distance here. I set distance here with this B0, B1 to represent the boundary between beams. So if we know the location perfectly, we can compute the switching timing perfectly. It should be around here, which should be at this exact point here, here and here. And if you have some estimation error due to the speed estimation error, if the speed estimation error is positive, that means we predict the train to be faster than it actually is. We will switch it too fast, and then there will be some portions of the beams that the train will not be aligned. Some portion of the coverage that is not aligned, as represented by this red arrow here. So in our model, we assume a sector model, antenna model. Sector antenna model, what it means is that it has 0 side lobes, so that the rate during this misaligned time is 0. So So what we need to do here is that we need to identify this time that it is aligned, and then we integrate using this timing as these integration intervals. So just doing that, we can do the same thing for the case when the speed error is negative. And one thing to note here is that it could be possible that the error is too large so that the beam is misaligned the whole time. It is shown here as in this figure. For example, it is misaligned at some point in that the base station assumed that the train is here in this dash line, where actually it is in this area. And at time t1, when the train actually moves into this area, it's all the base station predicted to be in this location inside the blue beams here, and so it switched to the blue beams, and the train will not get aligned at all. So in that case, we can compute it from this using this diagram again, and do some algebra to get these conditions for the case when the speed error is positive and when it is negative, as shown here. And with that, we can compute the average over this speed error, so that this is the upper limit and this is the lower limit, as we compute it here when the case that it is positive and it is negative respectively. And with that, we have all the formula we need to compute the total data rate, and we can do the optimization for our beam width. So these are the simulation parameters. We assume the pulse exponents of 2 because we have line of sight, which is basically just the free space. And we assume carrier frequency of 60 gigahertz. The bandwidth is 2.16, which is similar to that of 802.1180. And we assume different base station coverage lengths of 30, 60, and 120 meters. And the EIRP is set to the maximum limit of 40 dBm, and the vehicle speed is around 300 km per hour. And the speed error here, we computed for two different speed error. One is large at around 10%, and one is small at around 1%. So this is the result of the calculations. The axis, or the horizontal axis, is the beam width, and the vertical is the average rate here. And this case is when the speed error is large, and this case is when the speed error is small. You can see that when the speed error is large, the optimal beams is larger than 10 degrees, while when for the small errors, speed error here, the optimal beam is less than a few degrees. So we can also see that for when the coverage length increases, the optimal beams also increases. This is because of the estimation model here we have here is based on the source of the estimation error here is the speed error. So it will accumulate for a longer distance. So as you increase the coverage length, the accumulation of error also increases, and this means that you need to have a larger beams to have some buffer to absorb those error. And that's what we can see in the result here, that the optimal beams kind of get larger when the increases. So as a conclusion, we have shown that millimeter wave has the potential to provide a multiple gigabps service for high-speed trains. We have also shown that the beam sweeping based approach are unlikely to work due to the quasi-omni patterns. It will suffer from large Doppler spreads and so very small coherence time, and lead to the inability to decode the packet. And we propose a solution based on a beam switching approach that leverage the position estimations that could be possible through a train control system that can provide some position estimate. And using that solution, we don't even need to do beam training. And of course, we will not use quasi-Omni patterns, and so we will not suffer from the Doppler issue for the quasi-Omni pattern, as for the beam sweeping approach. And lastly, we also show how the effect of the position estimation error and the choice of the beam width. And the observation there is that wide beams suffer from low gains, but narrow beams are very sensitive to position estimation error. That's it. Thank you very much.